Yeah, thank you very much for the nice introduction. And thank you for inviting me to present at this nice workshop. I will talk about rate-induced tipping in asymptotically autonomous dynamical systems. And as I go, I will explain the meanings of these different words. It looks or sounds a bit technical, but it's probably less technical than it sounds. And what I will do, I will describe some theory, so that will link to the talk of Peter Ashwin from earlier this week, and give some examples of rate-induced tipping from natural systems. So the main motivation for my talk, and actually for my interest in tipping points, is this sort of global challenge that emerges from the document that was released in 1992, so already a while ago, by UNFCCC, United Nations Framework for Convention for Climate Change. And I just like to maybe draw your attention to two short paragraphs from this document. The first one says that the ultimate objective for us humans is to stabilize greenhouse gas concentrations at a level that would prevent dangerous interference with the climate system. So one thing that they worry about is dangerous levels of emissions or temperature, such that once you cross this level, we're going to be in trouble. So things will happen that would be undesired for humanity in general and for many people. Okay, and this is what you find a lot in IPCC reports, where the climate scientists worry about certain levels of CO2 emissions, certain levels of atmospheric temperature. But there is a bit more to this problem than just levels. And another big problem is that it's important how fast these things change. Okay, just excuse me for a second. Right, so the second paragraph actually links to this problem and says that such a level should be achieved within a time frame that is sufficient to allow ecosystems to adapt naturally to climate change. And adapt naturally means without our intervention or without our help. So there's two problems really, dangerous levels and dangerous rates. And it would be nice to have some idea how to analyze them from a mathematical modeling point of view. And in my talk, as the title suggests, I would focus almost entirely on those dangerous levels of change in dynamical systems, in natural systems. So the mathematical setting for my talk will be that of non-autonomous dynamical systems. So from a physical point of view, I have an open dissipative system that is subject to external disturbances. So this is my open system. The state that any given moment in time t is given by that vector x, which can be multidimensional. And the system is open. That means that it can receive some signals from the outside world. And I'm going to call them external inputs lambda of epsilon t. So these signals can change over time in a simple or very complicated way. And they will change with a certain time scale, which I'm going to denote here epsilon. So epsilon is going to be my rate or my time scale. And I will come back to that point later on. So it's a very important parameter. And the resulting mathematical model is this very simple looking differential equation. But the problem here is that this differential equation is non-autonomous. The right-hand side depends explicitly on time t via this external input lambda. Okay, so the question you want to ask about this problem is, what are the possible instabilities here in these systems? And we call them tipping points or critical transitions. And a lay person would describe them as sudden and large changes in the state of the system X, which are triggered by a slow and small change in the external input lambda. Now, this is a very well posed question, and you can apply this question to a lot of examples of open systems from natural systems like ecosystems, climate, even some technological systems, neurons. All those systems have this sort of strong nonlinearities. Now, the problem is that there is no well-established bifurcation theory for non-autonomous dynamical systems that would be able to capture all different types of tipping points or critical transitions. And what I will do in this talk, I will give you an idea of one of many different approaches possible that we developed with Pete Ashwin and other collaborators to actually answer this question. So this approach will have some assumptions and will have some limitations, and I'll try to explain, what the limitations are and what you gain, what you can achieve with it. So this approach is like as follows. I'm gonna look at an autonomous frozen system. So I'm gonna fix this external input and replace it with an input parameter small lambda. So what I have an autonomous system, x dot equals f of x, and that depends on lambda. So I'm going to look at the family of these autonomous systems, which is parameterized by lambda, and I'm going to look at the solutions for different but fixed in time values of lambda. And I will be interested in compact invariant sets of this frozen system. And these include equilibrium solutions, limit cycles, tori, chaotic attractors. I'm going to limit just to equilibrium solutions for this talk. So I'm going to denote them like that. And of course, they depend on the parameter lambda, because the right-hand side depends on the parameter lambda. You obtain them by solving this equation. And then there's one extra step. I'm going to actually define what we call moving equilibria. So this is a property of the frozen system and the external input. Now here, you replace this lambda with a time-varying capital lambda external input, and you define a moving equilibrium. So this is where the equilibrium of the frozen system would have been if the input did not change in time. Okay? So this is the instantaneous position of the moving equilibrium, and it's not a solution to the non-autonomous system. However, when epsilon is very small and the external input varies slowly enough, this moving equilibria can be a good approximation to solutions to non-autonomous system. Of course, we will be interested in the situations where the input changes slowly but fast enough so that the non-autonomous solution no longer can be approximated by this moving equilibrium. So the general approach is this, that we're going to relate non-autonomous solutions of the original problem to this moving equilibrium. I'm going to say, okay, where is the non-autonomous solution relative to the moving equilibrium, which is the position of the frozen system? That's going to be our approach. And when we deviate too much, we're going to quantify what we mean by that. And when you have rate-induced tipping, you're going to have a special deviation from that moving equilibrium. We're going to quantify it and define it rigorously and maybe state some results on that. So the outline of my talk is organized in those 5 points. I'm going to start with a simple example of what we call regular R-tipping thresholds from ecosystems. And this is work with my student Paul O'Keefe. Then I'm going to give rigorous definitions of R-tipping and regular thresholds. And that's work with Peter Ashwin and my other PhD student, Chan Zi. Then I'm going to describe compactification, which is a special technique which we developed with Chris Jones and Chan Zi. Okay? And this technique is to overcome this main challenge, that main obstacle of not being able to study instabilities in non-autonomous systems. Okay? So that will allow us to transform a problem of non-autonomous instability into something that we can handle relatively easily. And then I'm going to give some rigorous criteria for R-tipping with regular thresholds. And I'm going to wrap it up, say a few words about R-tipping due to quasi-thresholds, which are really, really challenging. And the techniques that which we develop for regular thresholds alone do not apply. We need to come up with additional techniques to study R-tipping due to quasi-thresholds. I will give some examples and highlight the main differences, and that would be more of an outlook for future research. So here comes the simple plant and herbivore model from ecosystem. That model was introduced by Martin Schaefer and collaborators in 2008. And this is the sort of link to the original paper. We have equation for the plant biomass P and herbivore biomass H. This is the first 2 terms on the right-hand side of the first equation. They describe logistic growth. And the last term, which describes foraging, that would be functional response, G, multiplied by the herbivore biomass. So this is basically herbivores eating plants. That's why I have a negative sign here. Now, as the herbivores eat plants, the mass of the herbivore is going to increase, okay? And there will be some efficiency here, and there will be some quality factor e to the negative BP. So as you have a very large plant biomass, then the quality of the plants decreases, and this is represented by this extra term here. And the last term is just mortality term. Herbivores will die for all sort of different reasons. It's a very simple model. Now, the important part here is hidden in this functional response function G. So this is the key nonlinearity, and the functional response function has two factors. The first one is the typical type 3 Halling response, and there's an exponential factor which makes this G non-monotone. So I have an example here of a typical type 3 Halling response. This is obtained for BC equals 0. And what those authors present, or what they suggest, is they argue that a more realistic response would be non-monotone and actually decrease at high plant biomass when the plants become either too tall for the animals to eat or become too dense and the animals are a bit afraid to go in. The same in oceans, when the plankton becomes too dense, then it's harder to penetrate and graze or forage. So this is the main idea, and this is a very important nonlinearity that will give rise to all sort of interesting behavior in this system. Okay, so this is the frozen system where the two important parameters are the maximum plant growth rate and M, mortality rate, are in red. For this talk, I'm going to vary this rate parameter R over time and at the rate epsilon. And at this point, I'm immediately stuck because I cannot use any bifurcation theory because my system is non-autonomous. So I have to make choices here. And the first choice is the first part of the main idea. And there will be 3 parts of the main idea in my talk. The first one is this. To make progress on this problem, I'm going to consider what we call bi-asymptotic constant parameter shifts. So these are the inputs lambda that are smooth, and they tend to a constant as time goes to infinity, and its derivative goes to 0 as time goes to infinity. So below we have an example of what I'm proposing here. I'm proposing an input that can be as complicated or crazy as you wish for finite time, but if you send time to either positive infinity or negative infinity, then lambda will sort of die out to a constant. Okay, that's what I'm suggesting here. And the rationale is that when you talk about tipping points, you look at the system, and system is, usually near an desired equilibrium or near a stable state where you want it to be. And then a disturbance comes in the form of, switching to a higher level or maybe doing some transient and coming back to the same level. And you want to ask, where would the system be after the disturbance is gone? Okay? So it sort of makes sense to assume that the disturbance dies out in the negative and positive time infinity. So this is going to be very important, and my rate parameter is epsilon. In papers, we often use R, so please don't confuse it. The reason we don't have R here because this ecological paper has R for the plant growth rate right there. Okay, so this sort of is going to be my external input, and epsilon is the rate or the time scale at which this input changes. Now, before I'm going to discuss these non-autonomous problems, I'm just going to look at the frozen system for the moment, where R here and M are fixed parameters, and do some classical bifurcation analysis for the frozen system, which I can do. So I can divide the parameter plane of this system, two-dimensional parameter plane, into regions of different behavior, and that's a 2-parameter bifurcation diagram. I have a transcritical bifurcation here in green. You see there is a saddle node bifurcation in blue. Then there is a subcritical Hopf in red, and there is a homoclinic bifurcation in H. And these emerge from the Bogdanov-Takens type 2 codimension 2 bifurcation point. So people who know about bifurcation theory, they sort of know that you can build a picture like that. It's almost like assembling a puzzle when you sort of compute different bifurcation curves. And here we have a pitchfork bifurcation point and Bogdanov-Takens bifurcation points, which are special bifurcation points. They give rise to other bifurcations. Now, as you move in that parameter space, say real systems parameter or inputs vary, and you move here. Okay? As you move, you may cross some bifurcations which are in solid, like this one, saddle node bifurcation, and then you're going to lose your stable state and have bifurcation-induced tipping. Now, if you go here and you cross this subcritical Hopf, which is in red, again, your stable state becomes unstable there is no continuity in the branch of attractors, so both bifurcations are dangerous, and you're going to have bifurcation tipping to some other alternative stable state. Okay? But what I'm suggesting here, let's fix a parameter path that starts at P1 and moves to the right. Okay? It's a very simple parameter path. It does not change. Actually, along that path, you don't cross any bifurcations whatsoever. That means that the stable equilibrium that you are interested in never bifurcates or loses stability. So you might ask, okay, what could possibly go wrong if I change R for a fixed mortality rate from P1 to some value along that path? So to the right, I have a simulation of what's going on when we do a non-autonomous shift from here to there. Okay, this is a tangent type of shift. So first of all, this is H, this is P, this is time. It's an extended phase space of my non-autonomous system. And the black lines are the moving equilibria. These are the equilibria of the frozen system when lambda is fixed to the value corresponding to its instantaneous value at time t. So you have a desired herbivore and plant equilibrium that sort of moves like this. Here is plant-only equilibrium that moves like so, okay, by changing R. And there is an unstable equilibrium here, which is a saddle that goes like that. Now, the blue curve is a solution to the non-autonomous problem when the shift is slow. So you see what happens during the shift. You deviate a little bit from the base equilibrium, but then you adapt and you converge back to that equilibrium. And we say that the non-autonomous system tracks the moving stable equilibrium. Okay, and this is exactly what you want. This is what you desire. Now, when you go slowly but a little bit faster, you see something quite different. The system deviates from the moving stable equilibrium and goes to a completely different stable equilibrium for no obvious reason. This equilibrium never bifurcates, never loses stability, but somehow the system deviates too much, fails to adapt, and makes a transition to a different equilibrium. Okay, so now what happened here? There were no bifurcations along that parameter path. My base state never loses stability or bifurcates, yet I have an instability in the non-autonomous system. So this is a genuine non-autonomous instability. We call it rate-induced tipping. And obviously you cannot analyze it using classical bifurcation theory because classical bifurcations tell you there shouldn't, nothing should really happen here. There's nothing special going on. All the bifurcations are elsewhere, and you're not crossing those dangerous bifurcations here. Okay, so the question arises of how can we analyze this? Okay, and I should mention that this pictures come from the paper with Paul O'Keefe. So to analyze it, I'm going to introduce this concept of Basin instability on this slide, and then I'm going to generalize this concept to threshold instability later on and link with the talk of Pete Ashwin. This Basin instability is absolutely essential to understand rate-induced tipping, and then later on, to also generalize to sort of more general problems. So there's three ingredients before I introduce this Basin instability. There's a parameter path in the lambda parameter space. So like that parameter space we had before, it was just two-dimensional, but you can imagine a 3, 4, 500 dimensional parameter space. In that parameter space, you sort of have a parameter path. And that parameter path describes how the external conditions, which are the input parameters, evolve slowly over time for a given system. Now, along that path, you want to have a stable equilibrium that never bifurcates or loses stability. Okay, that's, for example, that's the simple example of rate-induced tipping. Now, obviously, that means that there is no obvious loss of stability in the system. And you also want to look at the basin of attraction of this equilibrium along the path. I'm going to denote it B of E lambda. And then I can define basin instability. So suppose a hyperbolic sink, which is this stable equilibrium, varies C1 smoothly with lambda along that path P. That means that this equilibrium never bifurcates along path P. Then we say that the sink, E of lambda, is Basin unstable on the parameter path if there are 2 points on the path, lambda 1 and lambda 2. So remember, this lambda 1 and lambda 2 are the vectors, parameter vectors, and they have to be on the path, such that E at parameter lambda 1 is outside the basin of attraction of E at parameter lambda 2. So this E is the same equilibrium. As you change lambda, it's sort of continuous, but the position at parameter lambda 1 is not in the basin of attraction of the position of the same equilibrium at parameter lambda 2, which is a different parameter on the path. For people who prefer geometrical pictures, this is going to be illustrated on the next slide. And I can then also introduce the Basin instability region, which is something very useful for the bifurcation diagrams. So I'd like to illustrate this property of Basin instability in the 2D bifurcation diagram. And that's important because classical bifurcations don't give you all the information of what can happen there. Okay, so I'm going to define this Basin instability region as a set of all parameters lambda 2 for a given lambda 1, such that E of lambda 1 is not in the basin of E of lambda 2. So here comes the illustration of the whole idea. So I have the same bifurcation diagram as before. This is my path coming from left to the right. And I have three very special points, R negative, R star, and R positive. So what happens at R negative? At R negative, I have this phase space with two stable, so now this is HP, phase plane. I have a desired base state, which is the herbivore plant equilibrium here, which is stable. Here's another stable equilibrium, which is not desired. This is plant only. Herbivores are gone entirely. And there is the saddle equilibrium in between. The stable manifold of that saddle defines this special threshold, okay, which is basin boundary. The basin of this guy is in blue. The basin of that attractor is in white. Now, if I go from here to the end of the path, okay, the position of this equilibrium goes up. This is the picture here. So now this position of this at R plus, it's about 30, while it used to be below 20. And the shape and the position of the threshold changes as well. The threshold moves up. So this is the new situation, the new phase portrait for R equals R3. And that one in between for R star is a special situation. So the important thing to notice is that the position of the equilibrium at R negative is now outside basin of attraction of the position of the same equilibrium for R positive. See, this guy here now is there. So imagine if you change R instantaneously from R negative to R positive. You start at that stable state, then R changes instantaneously. So we are switching to this system, and the position of the old stable equilibrium is your initial condition. That will send you to this state where herbivores are extinct, and you have tipping. So if you, on the other hand, move along that path infinitely slowly, you're going to adiabatically follow all the changes in this equilibrium. You're going to stay very close, and you're going to end up here. So going slowly gives you tracking. Going infinitely fast gives you R tipping, or gives you tipping. So that means that there will be a final rate, somewhere between 0 and infinity, that gives you rate-induced tipping. There can be more than one, okay? But you know there will be at least one. And the whole point of this study is to actually figure out what are the values of these critical rates, and can we maybe say something how we can find them or compute them? Can we get a geometrical insight into what's happening for those critical rates? So now I'm going to use this idea of Basin instability to introduce this Basin instability region to my classical bifurcation diagram. And now I augmented classical bifurcation diagram with some information about non-autonomous instabilities. So this Basin instability is for the point lambda 1. You will get a different Basin instability for different starting point. What it tells you that if you take a path from lambda 1 to any point in the gray region, you're going to have rate-induced tipping if you go infinitely fast. And that means that there will be a final rate somewhere as you go from here to there along this path, or every path that you sort of come up with, that will give you rate-induced tipping. And we're going to have a rigorous result about it later on. And that's very interesting, because look at this system. This system is incredibly sensitive on how fast that parameter changes. That gray region of Basin instability is very, very large. And that's something that you wouldn't know just from classical bifurcation analysis. So now let's do those shifts again from left to the right and repeat what we did before, and now ask maybe a bit more questions. So again, my R changes from R negative to R positive as tanh. Okay, so this nonlinear shift. And I go from R negative and add some magnitude delta R. Okay, depending on the magnitude of delta R, tells me how much to the right I go from lambda 1. Okay, so I have this R tipping diagram now because I can do the diagram in the parameter delta and epsilon, which is the rate of change. So these are the input parameters. Okay, and you see that everything in the white I track. Here I have this pink region where I tip, and the black curve is the tracking tipping transition. This black curve becomes asymptotic to the Basin instability boundary, which is this gray line. So it tells you that this Basin instability is actually a very good concept. In general, it is sufficient for R tipping to occur in higher dimension. In this particular example, it is both sufficient and necessary for R tipping to occur. And what it basically tells you is that if you go very, very slowly, then you have to have a large enough magnitude of change to have tipping. However, if you sort of go a bit faster, then just crossing Basin instability already gives you tipping. So that's very interesting, this tipping diagram. And these diagrams can become very sort of non-trivial. And I don't have the time to discuss more complicated diagrams, but I would refer you to the paper with Paul O'Keefe, where he has examples of very non-trivial R tipping diagrams. The question I want to answer now is what happens when I track, I follow E3. When I tip, I move from E3 to E2, which is the other attractor. But what happens exactly at the transition? Well, it turns out that at the transition, you converge to an unstable state and you follow unstable state for as long as it exists. And that's very surprising. And first may actually seem very weird, okay? But it's not unusual that you can approach saddle states. It's just something very, very special. And that's exactly what happens. And people who study geometric singular perturbation theory or slow fast system, they are familiar with solutions that follow unstable states for a long time. They're called maximal Canard trajectories. So this is basically a bit of insight now. We are able to augment the classical bifurcation diagram with something about rate-induced instabilities, which is very, very nice. And we actually know what happens at the transition. And we can also add to the classical bifurcation diagram this R-tipping diagram. Now, the two main messages from this simple ecosystem example is that classical bifurcations do not capture all tipping phenomena, and we need an alternative mathematical framework for R-tipping or rate-induced tipping. So here comes the theory. I'm going to talk a little bit about regular thresholds and definitions of R-tipping due to crossing a regular threshold, describe compactification, and then talk about rigorous criteria for R-tipping to occur and maybe link them back to the example a little bit better. Okay? So this compactification is going to be the main point of my talk. I know that Pete Ashwin already talked a little bit about points 2 and 4. So I'm going to basically recall the main ideas and I will concentrate on this compactification concept, which is absolutely essential. It underpins sort of our theory of rate-induced tipping due to regular thresholds. So there we go. Now, the simple Basin instability that I just described for the ecosystem can be generalized to threshold instability. And I just explain what I mean by threshold and give some examples. So here is a definition of a threshold. So threshold, you want something that divides space into sort of, has two sides. So for example, a single line in 3D wouldn't have two different sides. Okay, these are not defined. But a two-dimensional plane in 3D, that would have clearly two sides. So we're going to define a regular threshold as a codimension 1 embedded orientable forward invariant manifold that is normally repelling. Okay, so that's a bit of a mouthful, but let me explain what this means. You want codimension 1 for this to have two different sides, and you want to be on either one or the other side of the threshold. That's what codimension 1 means. Embedded and orientable, it just to assume that it is nice enough. Okay, you want it to be embedded to sort of maintain that idea of two different sides and orientable. Okay, and this is where we can prove things. When you have manifolds which are not embedded or not orientable or neither, that would complicate things quite a bit. Okay, then you also want it to be forward invariant. Once you enter the threshold, you're going to stay there for all time, future time. Okay, and you want it to be normally repelling. So if you're on different sides, you sort of are repelled and you have locally different behavior. So this is what you imagine a threshold should do. You should sort of have two sides and you should do different things on different sides of the threshold. And that's a general definition. Now, because that thing is forward invariant, trajectory is going to the threshold through some boundaries, okay, will never leave the threshold. So they have to do something there. And while they're within the threshold, they probably converge to some attractor within the threshold. And this brings us to this definition of a regular edge state, eta. So we say that eta, which is a subset of the threshold, is a regular edge state if it is a minimal, compact, normally hyperbolic invariant set whose stable manifold contains a regular threshold. So basically think about something which is attracting within the threshold. So now here come examples. The first example, I have one stable equilibrium E1, another stable equilibrium E2, and the threshold is this unstable limit cycle. So this is at the same time a threshold and the edge state. Okay? So on this side of the threshold, you go to one attractor. On the other side, you go to another attractor. So if you cross the threshold from here, you're going to move to a different attractor. Okay, so this is typical example of a threshold which is multi-basin boundary, a basin boundary between more than one attractor. But if you go to the right, you have a slightly different situation. You have a threshold which is a basin boundary, but it is a basin boundary of just one attractor. This attractor E1. If you are below the threshold, you go straight to E1. If you're on the other side of the threshold, you also come back to E1 eventually, but you make this excitable excursion in the phase space. So this is an example of an excitable system where the threshold is given by theta and the edge state is a saddle point, which is an attractor within the threshold. Okay, so that's an example of a threshold and an edge state here. But the important thing is that you have two sides of the threshold, but the same basin of attraction on each side. There's only one attractor here. And then things can get more complicated or more interesting. There are some situations where you have quasi-thresholds. These are families of trajectories, we call them canards, that actually do not even form a basin boundary. And they don't have any regular edge states or any edge states for that matter at all. And they're very tricky to capture. Okay, so the theory that we're going to lay out here and that is captured by these definitions is the theory of regular thresholds. And the regular thresholds would involve multi-stable systems and excitable systems where you have well-defined excitability threshold. Okay, excitable systems of that sort, like neuron systems or some other systems, wouldn't be captured by our theory of regular thresholds. That's an important point to make. So now I can define R-tipping using these definitions. Okay, so regular R-tipping edge state. So this sort of ideas are for a frozen system. Okay, and I'm going to define the things.
Can I ask a question?
Yes, of course.
Yeah. So which of the conditions for the regular threshold is not present for quasi-thresholds?
Okay, so the regular threshold is, so it's first of all, it wouldn't be codimension 1, okay, because you have a whole family, continuous family of canards, so that's of codimension 0, okay, and then it has an inflowing boundary here, and it could have an outflowing boundary, so you can enter the quasi-threshold and you can leave the quasi-threshold, so it is not forward invariant either. Okay, but what it is normally repelling, okay, but it wouldn't be forward invariant, for example, and typically wouldn't be of codimension 1.
Yeah, but I mean, so for which conditions are allowed to be failed for that object to be still called a threshold?
Okay, I mean,
so this everything cannot fail, right?
Yeah. So let's say forward invariant. If you lose this, then you no longer have a regular threshold, all right?
Yeah, okay.
Yeah. So if you take a single canard, for example,
yeah,
or a piece of a slow manifold, which is unstable. So if you take the van der Pol oscillator, the middle piece of the slow manifold, which is the repelling slow manifold, has two boundaries when epsilon is non-zero, the inflowing and outflowing boundary. Okay?
Yeah.
Because you have this S-shaped. So this is the stable branch, unstable, and then stable. So the stable branch has two ends. And when epsilon is non-zero, these ends become boundaries. So that thing is not forward invariant because you can enter this unstable manifold and then you leave this unstable manifold.
Okay.
Okay. So there is no saddle equilibrium or anything that manifold connects to. But if you put a saddle equilibrium on the unstable slow manifold, then you have a regular threshold.
Okay.
So I hope that helps.
Okay. Yeah. Thanks.
Yeah. Thank you. So I mean, I'm happy to have interruptions and questions as I go. Okay. I'm going to have maybe some examples. There is time of quasi-thresholds, and at least I'm going to point you maybe to some papers that are useful in terms of kind of understanding the differences between regular thresholds and quasi-thresholds. So I'm going to define this for the non-autonomous system, okay? But you remember, it's a very special non-autonomous system, which is asymptotically autonomous. My input dies out to a constant at infinity. So the regular R-tipping edge state would be the edge state of the future limit system. So this is the edge state of the system when lambda goes to infinity and becomes lambda plus. Okay? Now I can define endpoint tracking. So we say the non-autonomous solution, x of t, endpoint tracks the moving sink if this solution limits to the future position of that sink, which is again an equilibrium of the future limit system, and it's an attractor of the future limit system. So normally this solutions always limit to some attractors. This is the normal situation, okay? And I call it endpoint tracking because I don't say what it does for finite time. I just have this property that my solution goes to E plus, which is the position of the stable equilibrium in the future as time goes to infinity. And then, I can define R-tipping due to crossing a regular threshold and critical rates. So what happens when you have R-tipping? And R-tipping is defined as a situation where your solution does not limit to the attractor of the future limit system, okay? So you go away from this normality. This is the normal situation. You limit to an attractor in the future, but when you don't, then you have R-tipping. Okay, so a non-autonomous system with an asymptotically constant input lambda undergoes R-tipping if there is a rate epsilon star such that for this rate, the solution limits to a regular R-tipping edge state, which is not an attractor for the future limit system. So this is the situation where you define R-tipping. You just go to something which is not attracting, okay? And now what happens past that critical rate? Two things can happen. This X can converge to a different attractor. This would be in a multi-stable system, or can keep on converging to the same attractor, and that would be in the excitable system with regular threshold, okay? However, when you have a regular threshold, there will be at least one value of this rate, epsilon, for which you do not limit to attractor in the future, limit to this saddle or a repeller even, okay? And this is how you define R-tipping. Now, if this epsilon star is isolated, then we call it the critical rate. And then we also distinguish between non-degenerate and degenerate R-tipping, irreversible and reversible R-tipping. I'm not going to spend too much time talking about this. This irreversible and reversible uses edge tails, and I think Peter Ashwin described this idea of edge tails. And I'm just going to maybe go back here, and you see here what I do. If I'm at this guy and I perturb below the threshold, I come back to the same person. Above the threshold, I come back to the same attractor. When I perturb exactly into the threshold, I limit to this edge state, which is not an attractor. Okay, so that's an idea. Here, if I perturb below the threshold, I come back to my attractor. If I perturb above the threshold, I go to a different attractor. So normal situations, you always go to an attractor. You may go to a different attractor, but sometimes you go always to the same attractor except for one or isolated values of the rate for which you go to some edge state, and this is the main idea. Okay. Now, see, in quasi-thresholds, you don't have any edge states because you don't have any saddles here. This is a monostable system. This is the only attractor for the system, okay? So the point is that, you know, for every rate, every single value of the rate, you always come back to this state. There is no edge state here, okay? And that thing is not forward invariant, and that's a problem. But for a moment, we could just focusing on these two guys, okay? Now I can introduce the second part of the main idea. We can use the compact invariant sets such as sinks and R-tipping edge states for the autonomous limit systems from the negative infinity and the future infinity, positive infinity, to analyze R-tipping in the non-autonomous system. So I know that when time goes to positive and negative infinity, I have autonomous dynamics with equilibrium points and maybe limit cycles and so on. The problem is that my system is not defined at infinity. So I would like to bring these infinities into the problem. And for this, I need to compactify. So compactification is sort of a slightly different way of extending a non-autonomous system. The usual way is we augment the vector field with this U, which is epsilon t, and rewrite my problem as an autonomous dynamical system with one extra variable U. Now you see that this usual approach doesn't work so well because that system doesn't have any equilibrium points, because U dot equals the rate, and rate is always positive. So that can never be zero. Okay? So and it's also defined on Rn cross R and has unbounded additional dimension U. Now compactification is a process that uses a different dependent variable, it's S instead of U, to make the additional dimension compact. So I want this additional dimension compact, bounded and closed. And then, you know, then I can start doing something useful with this system. It's a three-step process. In the first step, you have a nonlinear coordinate transformation. So you augment the vector field with S, which is some function of time, which is bounded. So say, for example, a function like that. Your time is in R, and S is between -1 and +1, and doesn't include the ones, obviously, okay? So this is sort of the type of coordinate transformation we will use, okay? And in the second step, we would like to continuously extend the augmented system here to include the vector field from positive and negative time infinity. Okay? So we're going to bring S +1 and -1. So the -1 for S corresponds to negative time, +1 for S to positive time infinity. Okay? We're going to bring that continuously into the problem. Now the problem is defined on Rn cross that closed interval, -1, +1. Now there's a question of how you choose this gamma of S. So you have to choose that gamma of S suitably, right? And if your inputs decay exponentially, you can actually solve the problem with a very simple equation like that, alpha times 1 minus S squared. And I say for n exponential decay that works. You can have any number of inputs that decay exponentially, doesn't matter. Lambda can be a vector from Rd, no problem. Just single equation fixes the problem, okay? Like I mentioned in the tutorial last week. Now it's a parameterized compactification. We have this parameter alpha, which I need to adjust later on. So then I go to the third step. I have continuously extended my problem to infinities, but I also need that the system is actually differentiable at infinities. So there is no guarantee that that system is C1 smooth at those added ends of the interval. So there is a theorem here which tells you that the augmented and extended vector field is C1 smooth on the extended phase space, or compactified and extended phase space, if these two conditions hold. So the second condition is very fundamental. It tells you that you cannot compactify faster than exponentially. And you can check it yourself that functions which are super exponential, they would violate this condition. But the first condition tells you that you cannot compactify faster than the decay of the external input. Okay? And how do you do that? Well, you adjust your lambda such that this condition is satisfied. And you adjust the simple compactification parameter alpha so that everything is smooth enough. And why do I want it to be C1 smooth? Because I would like to work with stable and unstable manifolds of this equilibria from infinities. And I need to use a stable manifold theorem, and that requires C1 smoothness. So this is sort of laid out in details in this paper with Chris Jones and Chun Zi here. Now, this is what happens when you apply compactification to the ecosystem model. On the left, you have the extended non-autonomous problem, okay, on R2 tag cross R. h, p, and the time. This is how you expand. There is no equilibrium points. You can define a two-dimensional R-tipping threshold that changes over time. And this is the situation that we had before. Now, if you go to the right and you look at the autonomous compactified system, this is defined on R2 cross this closed interval. So instead of t here, you have s from -1 to +1, where the ones correspond to infinities. At infinities, you have those invariant subspaces here, which correspond to autonomous dynamics from infinity, because lambda dies out to constants at infinity, okay? So you see you have your stable equilibrium here, another stable equilibrium, and the saddle at -1, and in the future infinity, you again have this guy, which is saddle, this is stable, and this is stable within the subspace. However, now the important point is that this S has a dynamics when you go from -1 to +1. So you introduce unstable direction, the third direction, for each equilibrium here. So these two attractors become saddles. This saddle remains a saddle, okay? But it has a sort of two-dimensional unstable manifold. Now, each of these gains one stable direction extra in the third dimension. So this attractor remains an attractor, this attractor remains an attractor, and that saddle becomes a saddle with a two-dimensional stable manifold. So you have one stable dimension from here and another from S, okay? So now this E4 plus would be the edge state for the regular R-tipping threshold, and the regular R-tipping threshold would be the stable manifold of this saddle, which is now two-dimensional. I don't have it plotted here because it would become a bit too complicated. But now I have a two-dimensional R-tipping threshold as a stable manifold of the saddle. Now, what are these trajectories now? There's different trajectories for different rates. I can plot what they are. So there's a big improvement now because I introduced some equilibrium points and I can start doing some regular dynamical systems, autonomous dynamical systems. And it's an autonomous problem, by the way, this compactified system. So now all those solutions are one-dimensional unstable manifolds of that E3 negative that used to be an attractor, but now it's a saddle when you embed it in the compactified system. So you see for the low rate, I go to this attractor. For the higher rate, I go to another attractor. But at the critical rate, this unstable manifold connects saddle E3 negative to the saddle E4 positive, which is the edge state. So the critical rate trajectory becomes a heteroclinic orbit from one saddle to another saddle in the compactified system. And this is great because I have reduced a rate-induced instability, which is a genuine non-autonomous instability, to a heteroclinic connection problem in the compactified system. And computing heteroclinic connections is not an easy thing, but we know how to handle them. We can use methods such as Lind's method and even do parametric continuation of heteroclinic orbits. And the reason why R-tipping diagrams were so nice and smooth is because that's exactly what I used. We compactified the problem and we did a continuation of a heteroclinic orbit in parameters to get the boundaries between tracking and R-tipping. So this is basically what you gain using this simple example. Now there are sort of more general statements. I just want to very quickly go through them to say what we've done on the theoretical part. And we basically given rigorous and easily testable criteria for R-tipping in situations when the base attractor is a sink, so an equilibrium, and the threshold is a regular threshold. Okay, this is where we can prove things so far. So there's two results. The first is a theorem. And what the theorem does is it takes very simple criteria from the frozen system and makes statements about what happens in the non-autonomous system. And that's actually quite nice, because if you think about scientists, natural scientists or ecologists, they would like to study those rate-induced tipping. I mean, rate-induced tipping represents, in a way, failure to adapt to changing external conditions. It's one of the most important instabilities in climate or ecology. Yet it's impossible to really pin down using classical bifurcation theory. So it would be nice to have some very simple criteria. And that's what we've done. We've sort of made statements about non-autonomous rate tipping in terms of simple properties of the autonomous frozen system. Okay? So the first one says that threshold instability of a hyperbolic sink in the frozen system is sufficient for the occurrence of R-tipping in the non-autonomous system for a suitably chosen input. So when you have a threshold instability, you can choose an input such where you have R-tipping. Okay? So this is when you choose the inputs. How about when your input is prescribed or given? When the input is given, then we need to introduce a concept of forward threshold instability, which is a bit like threshold instability, but not in parameters, but in time. And parameters vary in time. And when you have forward threshold instability, then it is sufficient for R-tipping to occur in the non-autonomous system with either this given input, but change in epsilon, or some parameterized input, where you reparameterize time of the given input. Okay, so that's the main result. And these results extend our previous study from one dimension to arbitrary dimension. And they also allow us to identify different R-tipping cases in arbitrary dimension. So this is the paper about one-dimensional problem. Now, the second result here is a proposition, is a more of a computational result. And it says that you can transform this R-tipping problem into a heteroclinic connection problem. Okay, so this is autonomous compactified system criteria. Now I'm going to make statements about rate-induced tipping in the non-autonomous system using the property of the compactified system. So this I have to do a little bit more. I have to compactify first my problem. And I have non-degenerate heteroclinic connection to the edge state in the compactified system is both necessary and sufficient for R-tipping to occur in the non-autonomous system. So this is very useful as a method for computing critical rates and R-tipping diagrams. You just look at these heteroclinic connections and you deal with them. And they tell you about non-degenerate R-tipping. So these are the main results. And of course, there's this, I already had a question about the quasi-thresholds. I'm going to use maybe the last 5 minutes to say a few things about quasi-thresholds and maybe give an example if there is time. So this is work with Pete Ashwin and student Owen O'Sullivan and my colleague from Cork, Kieran Mulcrone. Now, how about quasi-thresholds? Okay, so rigorous testable criteria are work in progress. And the way Pete and I attacked that problem was we introduced a third part to the main idea. So we have inputs that die out. That was the first part. The second part was compactification, which worked really great. But these two strategies alone, they don't work for quasi-thresholds. They're not good enough. Okay, so you need to bring a third strategy. And the third strategy is some special concepts from geometric singular perturbation theory. This is theory which you use for multi-scale systems or slow, fast systems. Okay? Now we are still working on it, and it will be a while before we have rigorous statements for quasi-thresholds in arbitrary dimension. But meanwhile, there are some very interesting examples. Actually, funny enough, the first example of rate-induced tipping, the paper we wrote in 2011, composite bomb instability paper, has a quasi-threshold. Then type 3 excitable neurons also have quasi-thresholds. So this is the paper by John Mitri from Australia and collaborators, okay, from 2013, which is actually quite soon after our composite bomb paper. And more recently, there are a lot of examples of problems in ecosystems with quasi-threshold. So one paper with Ulrike and Anna here, and there is a paper from Partha, and I don't know whether the first author was his student or collaborator. That's a very recent paper from 2022. Okay. Now, maybe I'd like to tell you a little bit about the paper which we just finished right now, about to submit maybe in a week or so, on zombie fires. And if I can see if I can share a new slide here, yeah. Okay, there we go. So the zombie fires, they occur in peatlands, and the peatlands are a special type of soils where you find usually in northern hemisphere. These are the black and gray dots here, right? And they are very temperature sensitive and they are bioactive. So what the map shows is where you have peat or turf or peat soils. This is around the equator where you have forests, and also in the northern hemisphere here, especially in Siberia. Now, the color scale is the rate of global warming, atmospheric warming. And you see that, the strongest warming is in the northern hemisphere. This is where a lot of peatlands are. So this part of the world warms very, very fast, and you have soils which have a lot of carbon content and they are very sort of sensitive to the temperature changes. So that's a problem, you know, that's a possible tipping point. And there's the zombie fires that actually, they come up a lot in Siberia, that disappear for winter, and people think that they are taken out, they put them out, but they reappear in the spring, and that happens year over and over again. So they happen underground. There is this active layer of peat soil underground. It's very difficult to put out because you can't just pour water on it. You know, it's not a surface fire, it's underground fire. Then it disappears over winter and reappears again, and hence the name zombie fires. So we used the compost bomb model, okay, which is the model just at two variables. This is the soil temperature and soil carbon content. It's a slow, fast system with a small parameter epsilon. So these two move on different timescales, and we modify this soil respiration function. So it used to be that this respiration function was unrealistic for large temperature of the soil, and we introduced this new function which sort of dies out at certain temperature. So this is due to the microbes, and the rationale is that the microbes don't survive temperature of 100 degrees, they sort of die earlier. And if you have flames, there are some other reactions and combustion, sort of onset of combustion processes present. For a moment, we just look at these microbes within the soil that can heat up the soil, but then they die out at higher temperatures. So this is some simulation of this sort of soil carbon model, okay, with this modified respiration function. And we take the global warming scenario, which is called RCP 2.6. It's a very stringent global warming scenario, saying that you have about 2 degrees Celsius increase since pre-industrial revolution, about 250 years until 2100. Okay? And 2 degrees Celsius average basically translates to 4 degrees in the Arctic, because you have this faster warming in the Arctic. So this is what we do. And this is the result. This is the moving equilibrium. This is the soil temperature for the moving equilibrium. And this is the non-autonomous solution. See, it sort of follows the moving equilibrium for the first 10, 20 years, but then just goes up to a very high temperature, which is reminiscent of this zombie fire, and stays there for about a decade. During that decade, all the carbon is being slowly burned, and then, you know, everything goes down to a lower temperature. So, you know, it's very difficult to put it out because this naturally actually stays for many, many years, and it's hot. And you can do something similar when this is the mean temperature. Okay, so this is global warming, this is climate change. But if you do weather, annual temperature, so, you know, you have these oscillations between summer and winter. By the way, this is in this location in Siberia, which is called Chersky, where that arrow here is. And we actually use the real data from that location. Okay. So if you do that, if you have this hot summer anomaly or a summer heat wave, this is sort of the moving equilibrium in black. This is the non-autonomous response, follows the moving equilibrium. But the moment you have the heat wave, you again have a rate-induced tipping to this metastable zombie fire that lasts for about a decade and then sort of dies out. So we can try to maybe do some simple inputs to sort of mimic global warming and hot summer anomalies or summer heat waves, do the compactification, and this is the compactified phase space, okay? This is the past limit system has only one attractor, which becomes a saddle. The future limit system has one attractor, which remains an attractor. This is the moving equilibrium. If you move slowly, you deviate a little bit, but nothing happens. That's the green solution. If you go slowly but faster, you have this transition to very high temperature. At high temperature, now you see the carbon content decreases to 0. So while you're burning carbon away, you're releasing into the atmosphere. Once all the carbon is burned, you come back to that future attractor. So there is no edge state here. For any rate of change, you always limit to the same future state, and it's difficult to pin down. And that's a problem with quasi-thresholds, okay? So if I introduce this slow manifold, because the system is slow fast, then you can see I have a stable sheet, unstable sheet here, and the hot metastable state, which is another stable sheet, a bit like the van der Pol oscillator, and that explains this behavior, okay? So what I have in red is that zombie fire, this is tracking, and in blue, we have what we call canard trajectory, which is a maximal canard and follows this unstable slow manifold for the longest time. It enters at this boundary, leaves at that boundary here, and then comes back to this E plus. So this is basically the challenge, and this is the R-tipping diagram. You replace critical rates with critical ranges of the rate. So sorry, now the rate is R, you see. Now this cyan band is a critical range of R. You don't have a unique critical rate from tracking to R-tipping. You track in the green, you R-tip in the red or pink, but you have a band of rates between. And it's more complicated. It can be a simple band or a complicated band with this R-tipping tongues coming up here. If I increase the magnitude, I'm going to have more tongues accumulating on top of each other. So I don't want to say much more about it at this stage. Okay, so what I would like to do is sort of maybe refer you to the paper of Owens on those zombie fires, if you want to understand those sort of details of what's going on for quasi-thresholds. And there is a good discussion of differences between quasi-thresholds and regular thresholds. I think it's for me time to summarize. Classical bifurcations, they don't capture all tipping phenomena. This R-tipping is a genuine non-autonomous bifurcation that describes failure to adapt. Like saddle node bifurcation would be a catastrophe. A hop of bifurcation would be the onset of oscillations. And if you look at non-autonomous bifurcations, this R-tipping seems to be a very basic sort of instability which you find almost everywhere, and it describes this failure to adapt. So it's important to study this. Now, what we did, we introduced this asymptotically constant inputs that give you asymptotically autonomous dynamical systems, which are in my title. And we were able to prove some general results with easily testable criteria about R-tipping due to regular thresholds. And we are able to reduce the problem to heteroclinic orbit in the compactified system. In the future, it would be nice to understand what happens when you tip from non-equilibrium attractors. And Peter Ashwin already discussed this a little bit. And we have some papers, and there was some interesting tipping mechanism already when you tip from limit cycles, but I don't have the time to talk about it now. And of course, you know, there's an important field, which is to understand rate-induced tipping due to quasi-thresholds. And this is still work in progress. Thank you very much for your attention.
Thank you. Thank you, Sebastian, for this illuminating talk. Question, please.
So I have a question about 2 slides before where you had shown this
okay.
quasi-threshold picture.
Yeah. So the quasi-threshold, right?
Yeah. No, I think it was just a couple of slides before this.
Okay, so we hold on a second. So we because I'm now switching between 2 different files. So just go.
Okay, where you had shown this the canard, and you were saying
yeah,
slowly.
Yeah, that's right. So let me just go and share the right thing. Yeah, sorry. So I did it in a smooth way, so you guys didn't realize that I was switching between different files. But that's what was going on here. Now everybody knows. Okay, I think now that's the one, right?
Yeah, this one. Yeah. So I guess, I mean, you showed by hand that with your mouse that it kind of moves slowly along the canard.
Yes.
And I guess I see that probably that's where the geometrical singular perturbation theory comes in.
Yeah,
but
exactly.
How generic is that, in the sense that you mentioned that quasi-thresholds, the ideas from geometric singular perturbation come in, but this, where do these slow or fast time scales come out from?
Yeah, so you usually you have several different time scales. Like this problem has 3 time scales, right? And the slow time scale, it always comes from the forcing. Because the funny thing about rate-induced tipping is that people think that you have to force the system very, very fast. But actually, sometimes you have rate-induced tipping when the forcing changes even slower than the natural timescale of the system. Because you have to compare the rate of the forcing with the rate of the movement of the moving equilibrium. And that equilibrium can move very fast. So there's one slow timescale comes from the forcing. And in this case, the system is slow fast. So the system itself has a slow timescale and fast timescale. That's why you have 2 slow timescales and 1 fast. And the slow manifold is 2-dimensional for that reason. Okay. Because there is a slow timescale from the forcing. This is given by S, which is the compactified variable of the forcing. And it's also given by by the carbon, which is the slow variable. And the temperature of the soil is the fast variable here. So you usually have a slow fast system when you have a slow forcing.
Okay. Yeah.
So any other question?
Yes, sir. Thank you for this insightful talk. I would like to ask you one question that is there any difference between basin instability and threshold instability?
Yes.
Can you please clarify?
Yes, that's right. So I'm gonna now, how do I do it in a clever way? I was able to, yeah. So, yeah, I can switch now nicely. So I'm gonna go back to here. So the basin instability here, for this example, would be when you go from basin of one attractor to the basin of another attractor. Okay, and that was the example, ecological example. Here, you don't really have a basin instability because you go from basin of attraction of one attractor to the basin of attraction of the same attractor. So that's why we call this threshold instability. Because this threshold is a basin boundary of just one attractor. Okay, and in this case, you will have threshold instability for quasi-thresholds, where the quasi-threshold is not even in the basin boundary. And again, there is only one attractor in the system. So typical basin instability, you think about the basin instability when you go from the basin of one attractor to the basin of another attractor. But you can also cross some thresholds from the basin of one attractor to the basin of the same attractor. And as you cross it, you can have some special behavior and you go from simple responses to excitable responses. So this is what we would call threshold instability, basin instability here.
Thank
for
you.
multi-stable systems.
Yeah, and another thing I would like to know that when we, the region of basin instability, when we construct that, is it dependent, the size of that region, is it dependent upon the functional form we are taking for the forcing? Yeah,
so absolutely not, because if you look at the definition of the basin instability, it only has the parameter path, yes, and the basin of attraction. Okay, so you have a path. It doesn't matter how fast you go along the path. So the form of the forcing is not important when you construct the basin instability. You just need a path in the parameter space. And that path, if you have the starting point, you have the basin instability, and a different starting point, lambda 1, will give you a different gray basin instability. And then what you're saying, if you now move along the chosen path with a certain function like the one here, or you can choose a different one, then you're going to have R tipping. But this is independent of the function with which you move along that path. So it's a simple concept. You don't need that function. Yeah.
Okay. Thank you, sir. Thank you.
Hello. So Sebastian, I have one question. So these are mostly studied in like smooth functions, right?
Yeah. Okay. So a way of maybe to anticipate your question, and I may be wrong. You can think of the concept of basin instability, where you just compare two values, lambda 1 and lambda 2, which are the value, for example, here and the value there. You can actually think that basin instability is defined for a very special input, which is piecewise constant and discontinuous. It switches instantaneously from R negative to R positive. Okay, so you have this discontinued input. And then what you say, okay, now in real life, I want to move along that path continuously. So you regularize this discontinuous input and you use something which is continuous and regular. And then you try to find the critical rates.
Okay. And in these basin instability cases, so let's say if there are ecosystems which are having fractal basins.
Yes.
So in the case of fractal basins, then what we can anticipate?
Yes, okay, so this is that the results don't hold, because then then the threshold is not embedded anymore, okay, and it's not a regular threshold, this chaotic this fractal basin boundary. But what you expect, I think, you like for quasi threshold, you have this band of critical rates, and I think for fractal basin boundaries, what you're going to have, you're also going to have a band. Let's say it's going to be tipping, tracking, but you have a band where you have a intermingled tipping with tracking, but intermingled like in a fractal way that you can't really decide whether you tip or track. So you go from tracking to sort of not knowing whether you tip or track, and when you add a noise that's sort of going to be smeared out, it's going to be probabilistic, and then you go into R tipping. There will be a range of rates.
Okay, so is there any study available, similar sort of study?
Yeah, I think there is some. I think that Ulrike has a paper about shifting chaotic attractors. Okay, but then that the base state is an attractor, and I don't remember whether the threshold is fractal in that example. I will have to check it. Okay, you may actually know that paper as well. You can check this. And there's a recent paper about the ocean circulation using a medium complexity model. So there was about thousands of ODEs, ordinary differential equations, and they don't know what the basin is, but they get some strange results for the rates that look like fractal, and they think they have a fractal basin boundary in this medium complexity climate model. Okay. So I think it would be nice. These are nice questions. I don't think they're explored to full extent, where you tip from something which is oscillating in a regular or irregular way, like limit cycle torus chaotic attractor. And also when the thresholds are very complicated. I think we know these cases are there. There are some very few examples, but I don't think there's a lot done on that.
Okay. And I have one more question. Like we are also doing something similar. Let's say if we just consider this consumer resource model that Ulrike has considered in her paper, even we have considered in our paper, just this Rosenzweig-MacArthur model. Yes. So what we see that if I just calculate equilibrium point for resource and consumer, then what will happen? The resource abundance will come independent of the growth rate, right? And then what we do, we give a rate to the resource parameter, but that is not only the steady state, the one variable. The steady state is basically this R star and C star. So that's why sometimes I get confused that probably the first paper by Peter Ashwin, when they say that, and I also receive in reviewers also say that you are not supposed to give a rate to the bifurcation parameter. So that sometimes confuses me.
Okay, so I'm not sure that I understand the question of what the reviewers say. So generally what happens is that you have an autonomous system with parameters, which are input parameters. Mm-hmm. And then you say, okay, now one of the input parameters changes over time. And then you make it a time-dependent function, and then you have a parameter, which is a rate, that controls how fast it changes. So this is how we would normally do it. But okay. Are you doing this differently? Are you trying to say that you do it differently?
No, so I do in this almost similar way, but sometimes I get confused because there is a paper by, I don't know, you have seen or not, by Chris Clemens. So he talks about something called a rate of forcing. So what he does here, in a continuous way, we give a rate. So we say dr by dt equals to lambda, but what he does, he does it a discrete way. He will say that r equals to lambda t plus r naught. So he basically, what he does is the same thing. And he says that if you give a rate to the bifurcation parameter, that what happens, if it is fast, then you will reach the threshold point in a less time. And if it's slow, then it will take more time. So sometimes then...
Oh, yes, but then he's not talking about rate-induced tipping. He's going through bifurcation. And everything that I described on those parameter path, when you make the parameter time dependent, you never cross a bifurcation.
Point, exactly.
And that's the main difference. So when you go across a classical bifurcation, when you change the bifurcation parameter, then of course you're going to have bifurcation-induced tipping. And this is very sort of, it's obvious, right? Everybody knows that if you cross a bifurcation, you lose an attractor, you have to go to a different attractor. Now, the rate-induced tipping is different because you never lose your attractor, but yet the system makes a transition to a different attractor, or maybe for some finite time goes far away from your attractor. Okay, so that's the difference. So I think he was describing bifurcation-induced tipping more than rate-induced tipping. But sometimes you can have this situation where, I'll see if I can sketch it here. Okay, that's why this is not trivial. Because you can have a situation like that when you have two bifurcations. Okay, like this. I think that's going to be the quickest. So, and this is the parameter.
Okay.
So I'm gonna maybe some axis. So this is parameter, and this is x. Okay.
Yes.
So there, I don't know what you can see.
Yes,
Yeah.
I can see.
So you start here and you vary the parameter. If you vary slowly, you're gonna drop, and you're gonna have bifurcation induced steeping because you went through a bifurcation.
Yes.
Okay. But if you go a bit faster, you're gonna do this, and then you're gonna enter this manifold, and then you're gonna go to something which is not an attractor.
Okay.
Okay. And then if you go very fast, you're gonna switch to this one. So this is a combination of bifurcation-induced steeping and rate-induced steeping, because the rate, as you vary the rate alone, you switch from going to this attractor in the future, if you go slowly, to going to that attractor in the future if you go very fast.
Okay.
And it's a fun rate-induced steeping. We actually, you sort of follow something when you go fast rather than slow, you see? And maybe that's what they mean. But it is not trivial. So you can have other situations. That's why it's important to define rate-induced steeping that in the future you limit to something which is not an attractor. And this is going to be the transition from this situation to that situation has to go through a situation where you go along the unstable state and limit to something which is not an attractor.
Okay.
And then you have rate-induced steeping. But this example would have both bifurcation and rate-induced steeping. Yeah.
Okay. Okay. Thank you. Thank you, Sebastian, for developing these wonderful theories. Thank you so much.
Okay. Well, it's nice. I should say nice seeing you. I wish we could meet in person, but maybe some other time.
Yeah, thank you. Thank you so much.
Yeah. Okay. Thank you so much.
Any other question? Any other question? No.
Okay.
Thank you very much. So,
yeah. Thank you. Thank you, everyone. Bye.